Everyone, check. In coordination compounds, we discuss about two types of salts. One is addition salt, the other one is simple salt. Am I audible? This way. Within addition salt, we see two types, double salt and complex salts. When I use the term double salt, they will retain their identity in solid state, but they lose it in aqueous state. For instance, if you take K2SO4 dot Al2SO4 thrice, one second. You can see K2SO4, Al2SO4 thrice dot 24H2. This is called potash alum. This one is carnallite and this one is Morse salt. In fact, for our syllabus, only these three are important. So learn that how the structure looks like. Now, as the Morse salt is been added to sufficient water, now you see it has lost the identity being ferrous sulfate or ammonium sulfate. Instead, in water, now it is identified as only basic ions. Fe plus 2, SO4 2 minus, and NH4 plus as basic ions. Now, these basic ions can be identified as various tests, and that's what you can do it with K2SO4, with potash alum as well. So, if you have K plus, please everybody keep on one. Check. K plus can be identified using platinic acid. H2PtCl6 is platinic acid. It is a colorless acid. As soon as we add K plus to it, it will convert into an yellow color PPT. It is confirming the presence of potassium ions. Okay. Similarly, Al plus 3, if this solution is been added to NaOH, we will see a white gelatinous precipitate, which confirms the presence of Al plus 3. If you have sulfate ion in the solution, you add some barium chloride solution, salt, and if you get white color PPT, that confirms the presence of sulfate. Okay. So if you are able to identify the ions based on what is present in the double salts, then that means you are able to check the basic constituent of those elements. It suggests that it must be a double salt. A complex salt is the one which will retain its identity in solid state as well as the aqueous state. For example, if I take FeCl3 aqueous solution and I add KCN to it, first it will start becoming FeCN thrice precipitate. And as you keep further adding KCN, it will convert into a colorless aqueous complex. This is in complex, sorry, colored aqueous complex. Now these ions are not detecting Fe plus 3 and Cn minus in aqueous solution, which means whatever iron and cyanide bonds are, those are still retained here also. They are not being identified separately. So if we add this to the solution, for platinic acid, it will give you the confirmation for potassium. But to identify iron plus 3, if I try to use SCN, I won't get any type of precipitate. Neither if I'm using any copper here, right, I will not be getting anything for the presence of cyanides. Therefore, here we can say that these ions which are present in the bracket, they can't be detected as a separate ions. Okay? Such kind of salts, what we call them as complex salts. Got it? Now within complex salts, we can identify them as, perfect and imperfect ions. Here, few questions, before going into that, few questions which were asked earlier in JEE. where they might have asked about what happens on heating. This could also be added here. So check out what is the type of questions that could have been come. See, usually if you notice Carnallite, KCl dot MgCl2 dot 6H2O, if we heat it, we expect this to get KCl plus MgCl2 plus 6H2. But this is not how it ionize into. This is not how it dissociate into. Rather, it will convert into KCl plus MgOH twice plus H2O. This for on further heating will convert into MgO plus H2O. So basically, you would be reporting KCl, MgO, and H2O, and not MgCl2. MgCl2 cannot be separated out. Okay. Similarly, if I take Na2CO3 dot 10H2O, in this case, when you heat, you will get Na2CO3 plus 10H2O. Why sodium is not forming oxide here, unlike magnesium, is polarizing power of Mg2 plus is much higher compared to Na plus. So when the polarizing power is higher, generally they end up forming oxides. Okay. First they'll form hydroxides, finally convert into oxides. Any metal ions, Fe plus 3, Cr plus 3, cobalt plus 3, nickel plus 2, right? Especially D block metals, they on heating, they cannot sustain as chlorides or sulfates or something. They'll always convert back to oxides. Yeah. So that is what we'll see now. So even if you have FeCl3 dot 6H2O on heating, it will convert into FeOH thrice as a precipitate plus HCl. And this on further heating will convert into Fe2O3 plus H2O. Even CrCl3 dot 6H2O, which is present, this on heating will give you CrOH thrice plus HCl, and this on further heating will give you Cr2O3. Okay. While if you take any type of alums, right? In case of alums, basic formula is M2SO4 dot M dash twice SO4 thrice dot XH2O. This is typical formula for alums. Here, M plus what we are taking must be a low polarizing power cation. So they should not form into oxides. Okay. Like Na plus, K plus, Rb plus, Cs plus, right? Tl plus, ammonium ion. These are low polarized cations. Okay? So which means Li plus cannot be taken here because Li plus will have sufficient polarizing power. Okay. While M plus 3 should have high polarizing power cations. That includes Al plus 3, Fe plus 3, Cr plus 3, indium plus 3, zirconium plus 3, iridium plus 3. They all will form various types of alums in this combination. Okay. By the way, where are alums used? Generally, alums are water soluble. They are water soluble. Okay. So and it is used in softening of water. Clear? And they are generally slightly acidic. Slightly acidic. You can see they have sulfate compound, sulfate ions. So they will be slightly acidic. Acts as coagulating agents. They act as coagulating agents. Okay. Clear? Right. Now, You must have seen what are the more salt, how it looks like, and other cases, right? Next, coming to this word, what are perfect and imperfect complexes? See, perfect complexes does not give test for constituent ions present within the bracket. Within the bracket, it will not ionize into copper, ionize into cyanide. Therefore, there is no presence of copper plus 1 or cyanide minus 1. Okay. So, if you treat with HCl, you will not see any precipitate of Cu2s. Okay. Other examples for that matter, if you notice, uh, if you add Cu, NH3, 4, and 2 plus, if I add slightly acidic compound like this one, I will not get any precipitate. Okay. Fe, F6, 3 minus. If I add SCN minus to this, I will not get any precipitate, which showcases that this is acting like a perfect complex. Why I took this example is that fluorides are very weak ligands, yet they will form a complex which cannot be ionized. So strength of the complex, strength of the ligands has nothing to do with how we can observe as a perfect or imperfect complex. Okay, right. Next, imperfect complexes are these which when added with H2S, right, will convert into CDS and AgNH3 plus. If you add it to I minus, Br minus, Cl minus, not Cl minus, in these two cases, it will act like imperfect. Now, is it possible that in some case it is perfect and in some case it is imperfect? Yes, it is. It again depends upon what is the solvent you are adding. For example, if I take FeF6 3 minus, if I take this and add it to OH minus, see in HCl minus, it is not making any change. But if you add it to OH minus, in this case, it will convert into this brown color PPT, which suggests that in this case, acting like an imperfect complex. Imperfect complex. So imperfect complex and perfect complex is subject to the solution what you are putting to. Okay. In some solution it may be perfect, in some solution it may be imperfect. Clear? Another case what you need to remember is that the reverse could be possible here. That is, if you have a precipitate on adding excess of ammonia, you would notice that AgCl will get dissolved, AgBr will get dissolved, but AgI will not get dissolved. Okay. Next. What are the main terms we need to understand in coordination compounds? Anything which is outside the sphere is called ionization sphere. Within the brackets, we call it as the coordination sphere, and it would have ligands, it would have central metal atom, and X represents number of ligands, which is coordination number as well. Okay, check. Ligands can be classified based on many types. One is charge, basically whether it is positive, negative, or neutral charge. Then based on density and so on. Typically, you guys need to understand one thing is that if you have a metal ion, some Mx plus, let's say, then this metal ion can be considered as Lewis acid. And if you have some Y moles of ligand, let's say, okay, this can be considered as Lewis base to form an acid base reaction of MLY overall X plus like this. And this is the complex salt. This is the complex salt. So complex salt can always be viewed as a reaction of acid and base. Okay. Next. Check out based on charge, what would happen. See, if you have positively charged, their name should always end with EM. We rarely have positively charged ligands. Only two of them which we mostly see is NO plus and this hydrazinium plus. NO plus is called as nitrocilium. This is called hydrazinium. Okay. Next, in case if you have negatively charged ligands, if you have an ide form, a salt ending with ide, we will write it as ido. Ate form, ato, ide form, ito. So chloride will end with ido, chlorido. Carbonate will end with carbonato. Bromide ends with bromido. Cyanide ends with cyanido. Especially for halides and cyanides, we can always use the old IUPAC name as well as the new IUPAC name. Ido is a new IUPAC name. Only O was the old IUPAC name, which is chloro, bromo, cyano. Okay, we can use that. Oxalate, we will use it as oxalato. Okay. So, like that, in case of neutral ligands, we will have something like H2O, which we call it as aqua. NH3, important word is here, we should have 2N, amine. Then En, which means ethylene diamine. Okay. Pyridine, which we write it as Py. Next, carbonyl, nitrosyl. These are also neutral charged ligands. Now, within negative charge ligands, we have a lot of list. You could notice that we have N3 minus, which we call it as azido, ClO2 minus, which we call it as chlorito, correct? HCO minus formato, OCN minus cyanato, here, SCN minus thiocyanato, and so on. Okay, these are all various names as clear. Right. Next, suppose here I'll come back to that. If you have these groups, these are the ones which we will using, which will be using a lot of times. And second classification is based on denticity. That is, how many number of electron pairs are being donated to the metal. If we call it as monodentate, that means we are giving only one pair. Like water, OH minus, H minus, these all compounds which I have written, they will only give one pair of electrons. Okay, they'll only give one pair of electrons. Next, bidentate. Bidentate as in they will have two donor sites. From two ends, they will donate. So in this case, ethylene diamine donates from two nitrogen ends. The charge on that is 0. OX, which we call it as oxalato, will donate from two ends of oxygen. The charge is -2. As it donates, it is able to make a 5-membered ring formation here. So this is also called a chelation. And chelation always brings extra stability to the complex. GLY, known as glycineto. This is called glycineto, where from one end it is NH2, from other end it is O minus as they connect. Charge is -1 in this. TMG. In case of TMG, the connection is both from nitrogen end, 5-membered ring here. It is dimethyl glyoxymeto and charge is -1. ACAC, acetyl acetaneto, connection is both from oxygen end, makes a 6-membered ring. Here it is 6-membered chelation and charge on that is -1. Okay, charge on that is -1. Clear? Now, few more things what we need to know. Okay, apart of that, we use something called flexidentates. Flexidentates. Flexidentate is another classification where we can have a connection from uh, two ends, right? If they are in a smaller chain, right? or we can have it in one end. Suppose if you have carbonate, double bond O, O minus and O minus. Metal is there. In such cases, this can make a coordination with both the oxygens, or it can make coordination only with one oxygen. So here it is acting like a monodentate. Here it is acting like a bidentate. Clear? So depending upon the demand of the metal, it might give a mono connection or a di connection. So such kind of cases are called flexidentates. So they show variable denticity. Okay. So the idea here is variable denticity. Variable denticity. Okay. Next. Next. If you have flexidentate, yeah, some more examples I'll write it down. SO3 2 minus, CO3 2 minus, SO4 2 minus, NO3 minus, NO2 minus, it can be NO2 minus also, correct? And EDTA also, EDTA 4 minus, EDTA H3 minus, H2, EDTA 2 minus. All these forms are flexidentate forms here. Yeah. Another one is S2O3 2 minus. This can also act like flexidentate. Okay. Yeah. Right. You need to understand, other than bidentates, we should also look at into hexadentate. So now this is important there when it comes to hexadenticity. How do we look into this? Check. When you have hexadenticity here, so you will see that EDTA, EDTA specifically, which we call it as ethylene diamond tetraacetate, will have six connections. One from this nitrogen. See, read it carefully. Ethylene diamine and tetraacetate. There are four acetate groups here. One, two, three, and four. These four are the acetate groups we have. Okay. And connection happens from two nitrogens and four oxygens of that group. That's how we will have five-membered rings, and connecting atoms are all oxygen, four oxygens and two nitrogens. Okay. And the type of bonds, you notice that N, M, and N. N, M, and N, we have one bond. N, M, and O, I have eight such bonds here, like this, like this. We can see eight such bonds we can have, four with one, like this, and four with another one, like this and like this. These are four bonds. OMO bonds, I have six of them, like this. So these are the various type of bonds which you will have it in this case. Clear? Yes. Few tridentates we need to know. Okay. One tridentate we need to understand is uh, tridentate, which you need to know. There are two tridentates I would suggest. One is this one, where we have nitrogen, and again another nitrogen here, and this nitrogen, this one. So basically here we have diethylene, diethylene triamine, diethylene triamine. And if metal is here, lone pair from here, lone pair from here, and lone pair from here will form. Okay. Another one is, you know, phenyl groups. If you, sorry, pyridine groups. If these pyridines are connected this way, this way, and these are all pyridine groups, and I have a metal connection here. So connecting from here, connecting from here, and connecting from here. This is also pyridine. So this is terpyridyl, terpyridyl, another case. These two are good examples of tridentates. When it comes to tetradentates, tetradentates, uh, you can always lie onto this one. We have CO minus, CO minus, CO minus. Okay. And nitrogen is also an element which you can give. So four connections you can notice. One is from nitrogen, oxygen, oxygen, and oxygen. Here, this is called N-nitrilo acetato, acetato, or we simply write it as NTA 3 minus, NTA 3 minus. Clear? Or we can also have more density with nitrogen here, like this, another nitrogen, like this, another nitrogen here, and one more nitrogen here. So metal, if you have, it can connect from this 4 ends here. So what do we have here? Triethylene, triethylene tetraamine form. Okay, triethylene tetra amine form. Okay. So these are few tri and tetradentates which you need to look into. Clear? Next. Now, look into this part. Generally, we learned what is coordination number. That is how many connections, ligand connections we can make. Especially if you come across these metal ions, right? We should have some clarity about how much amount of coordination they usually take. Copper can take 2 and 4. Silver can make 2. Gold can make 2 and 4. Mercury always 2. Cu2 plus can make 4 and 6. Ag2 plus will make 4. Pd2 plus will make 4. Palladium will make 4. Magnesium will make 6 always. Nickel 4 and 6. Iron 4 and 6. Plus 3 always 6. Cobalt plus 2, 4 and 6. Cobalt plus 3, 6. Al plus 3, 6. And rest all these higher oxidation state are all 6. So we must understand that how much amount of coordination is being observed in all these cases. Clear? And these are the ones which I told you. The one which I didn't write is this one. One is OFEN, OFEN, which is phenandroline. The other one is dipyridyl, right? So which is N connection, dipyridyl. Rest all we have seen it. This we just discussed it. NTA. Okay. Pentadentate if needed, but usually not asked. Check out on hexadentate. Okay. Next one is about chelating ligands. Okay. If you have any polydentate, would structure permit only two or more donor sites, right? Then metal donor sites to metal simultaneously, it will form a cyclic structure that is called as chelating compounds. So whatever we have discussed so far, those are all chelating ligands only, which can make a 5-membered, 6-membered ring and so on. This one is very important for us. What are ambidentate ligands? Now notice it, Cn minus can connect with Nc minus from C onwards or N onwards. So this would be ambidentate. NO2 minus, SCN minus, CNO minus, S2O3 2 minus, right? Usually ambidentates are always monodentates. Usually ambidentates are always monodentates, except in the case of S2O3 2 minus. Because this can act like a flexidentate, giving bidentate nature also. But it is still ambidentate because it can connect from sulfur end or oxygen end. Okay. Selenium cyanide here. So that is also ambidentate ligands. We learned what is flexidentates already, right? Now, the third classification is based upon what is the bond interaction between the ligand and metal. Okay. Now, if you notice, simple ligands only donate lone pair of electrons to central atom. Okay. So if you notice O2 minus, OH minus, F minus, these are all those simple ligands. Okay. Non-classical or pi acid or pi acceptor ligands. Pi acceptor ligands are those which do not donate the lone pair of electrons to central metal, but which not only donates that, but also accept the electron cloud from central metal atom. So specifically, if you notice carbon monoxide, cyanide, PF3 or PR3, etc., okay, you will notice that the metal from the from the back end, it will always support to the pi orbitals, pi star orbitals, or empty d orbitals. In case of PR3, it will have empty d orbital. So in those electrons will be supported. This kind of bonding is called synergic bonds. So it will make more of synergic bonds here. And that would be our non-classical or pi acceptor ligands. Those are pi acceptor ligands. Okay, clear guys? Next, this is how the metal bonding is observed. You can see. Read out few important statements here. Check. The metal carbon bond in metal carbonyls may be represented as donation of electrons, pair from carbon to vacant orbital of metal, which forms a sigma bond. So the first bond which we make, we call it as a sigma bond formation. The second bond formed by the back bonding is called dative bond. This arises due to the sideways overlap with the empty anti-bonding orbital, right, of the carbon monoxide. Thus, pi m d pi d pi towards carbon monoxide, that is the back bonding which you will notice. The filling of partially filled of anti-bonding molecular orbital of CO reduces the bond order of CO from the triple bond towards a double bond. Because if that bond is getting stretched as the anti-bonding is involved, the bond will start getting stretched, because of which the double bond character will start going towards, triple bond character will start moving towards double bond. This shown the increase in CO bond length from 1.128 to 1.15 in many carbonyls. CO accept back donated electrons from the metal atom into its vacant pi star orbital. Then we call it as pi acid or pi acceptor ligands. Other such pi acids remaining are this. Pi acid ligands like these accept the back bonded electrons into their vacant d orbit. Okay. Now, another way where you can notice is that pi bonded organometallic compounds like Zeus salt. This is Zeus salt. In case of Zeus salt, the cloud, the pi cloud which is present, that cloud itself will support as a sigma bond, right, with the metal central metal atom present. Okay, the pi electron density of alkene overlaps with the sigma type vacant orbital of the metal. The second pi bond formation, flow of electron density from the filled d orbital of metal into vacant pi star. So this is what I have written. See, these are the vacant pi star orbital, and metal will have this sigma star, pi star electron density orbitals. So they can make a bond here. So again, there is a synergic bond nature observed. So even in organometallic compounds with pi bonds, we will see this formation of uh, metallic bonds. Okay, synergic bonds. Here, right. Few important lines, I mean, which I have not written it here, but which I would suggest we should learn is first, see, if metal atom, metal atom, metal atom or ion, okay, involves its pi electrons, then we call we call metal ion or atom as pi donors. These are pi donors. So, in fact, pi donors, pi donors are all pi acceptors also. Pi donors are also pi acceptors. Yeah. Second thing, as metal ion, metal ion charge increases, increases, okay, pi acceptor, pi acceptor nature further increases. Yeah, sorry, pi acceptor nature slightly decreases, which means if I take FeCN6 2 minus and FeCN6 3 minus, if you compare these two, both cyanides are pi acceptors here. Stability wise, if you notice, this is the stability here. This is the stability. But if you compare the amount of backbone donation here, that will become weaker. But what increases is the sigma bond. Okay, sigma bond strength between metal and carbon increases strongly as charge on metal increases. Charge on metal increases. Okay, so keep this in mind. Okay. Now what we can do, generally, we can say generally, okay, carbon donors are the very strong donors compared to nitrogen donors, compared to phosphor donors, compared to oxygen donors, compared to sulfur donors, compared to, halogen donors. Typically, if you compare the connection from where they are, this is the uh, compounds which you will see. Okay. Yeah. Now, next thing, metal carbonyls. When you have metal carbonyls, when we talk about, they can make mononuclear connections, which means I'll have only one metal into it. There are no multiple metals. Like if you have NiCO4, okay, FeCO5. So there are only mononuclear connections here. Then we have polynuclear connections, right? Polynuclear connections, as in they could be two ways. Within that, again, we can have two ways. One is terminal polynuclear connections, which means something like bidentates. So manganese twice, CO10. Okay, manganese twice and CO10. The other form is bridged. The other form is bridged. CO2, CO8. Okay, this kind of case we have, then we call it as bridged form. Okay, clear? Some of the bridge forms which we need to learn are this first one, CO2, CO8. If you notice, cobalt, cobalt connection we have C double bond O, C double bond O. Then we have three CO connections here. Okay. So these two are the bridged carbonyls. These two are the bridged carbonyls. Mn2 CO10, if you have, the connections are between manganese and manganese. And then we have 5 connections on this side, 5 connections on the other side, like this. These are carbonyl connections with manganese. Clear? Now, important point here is all polynuclear complexes must have metal-metal linkage. Without metal-metal linkage, it does not exist. At least one must be having a metal-metal linkage. Clear? Okay. One important thing that is always asked in metal carbonyls is something called stretching frequency of a bond. Stretching frequency of a bond. Okay. Basically, it means frequency of oscillations, frequency of oscillations about mean position of a bond. Typically, stretching frequency is written in terms of mu wave number, which by formula is this. Not that you need to mug it up, you just need to know it. K by mu. K represents a force constant, which is same as a spring constant here. And this K value is directly related to bond order of carbon monoxide bond. Higher the bond order, higher the K value, higher the stretching frequency. Clear? So mu represent reduced mass of CO. Reduced mass of CO. Clear? Most of the complexes, when we learn it, we are not changing anything about reduced mass. So it is that K factor which is changing. Okay. So because that K factor changes, we will say the stretching frequency is different. Okay. And we know that generally bond order is directly proportional to bond energy, but that is inversely proportional to bond length in most cases. Okay. So I can say as tendency of back bonding, tendency of back bonding increases, tendency of back bonding increases here. Uh, metal carbon bond order will increase. Metal carbon bond order will increase. Okay. So which means metal carbon bond energy will also increase. Yeah. And metal carbon bond length will decrease. Sorry, here only I'll write. Metal carbon bond length will decrease. Okay. What is the resultant of this one? This will have CO bond order decreasing, CO bond energy decreasing, CO bond length increasing, and stretching frequency of carbon monoxide decreasing. Isn't it? Why? C related to this. Bond order of carbon monoxide will decrease. Bond order decreases. So what happens to the stretching frequency? It decreases. Clear? So in all these cases, please make sure relate stretching frequency always with bond order. Okay? Fundamentally, how it is coming, I hope all of you clear with that. Yes, once. Check out. In case if you have uh, metal with a carbonyl compound is present and some XM, but this has positive charge on it, then metal carbon monoxide bond order will be weaker, which makes which makes carbon and oxygen bond order to be stronger. Understood what I'm saying? Same way, metal, if you have negative charge on it, if you have some extra negative charge by which, then metal carbon monoxide bond order would be more, which decreases metal oxygen bond order, right? So, for example, if I give you Mn maybe CO6, right, with plus, and VCO6 with minus, and CrCO6 only, like this. It is A, B, and C. Metal carbon bond order. Which one will be more in this case? Which one will be more? B, then C, then A. Correct? Carbon and oxygen bond order. Which one will be more in this case? A, then C, then B. Based on that, which one will have more stretching frequency of carbon monoxide, right? If the bond order is more, then stretching frequency will be more. Huh? Clear? So remember it as a question. This would be a very standard question that could be asked. Okay, we should be able to address this. So I hope all of you got an idea how to discuss about the metal carbons. Okay. Since we are in the lines of metal carbonyls, here itself we will try to figure out how to use the VBT for understanding the hybridization within the metal carbonyls. Okay. Suppose we take an example NiCO4. NiCO4. Okay. Always try to write the configuration. First, check out what are the number of electrons present in nickel. Okay. So, configuration wise, it is 4s2 and 3d8. It is neutral in nature. Here, there is no charge on nickel here. So, the primary valency, which implies the oxidation state, primary valency implies the oxidation state is 0. Secondary valency in this case is 4, which is the coordination number. Now, whatever the electrons which are present in 4s, right, to make sure it gets hybridized, push everything to 3d. By pushing that, we'll be able to make 4s completely empty and 3d has 10 electrons. Now, since 3d has completely filled orbitals now, 1, 2, 3, 4, 5, 6, 8, 9. This is 3d. Now 4s is empty, 4p is empty, 4d is also empty. I need to only accommodate 4 ligands. So I would take these 4 orbitals, combine them to make it sp3 hybridized orbital. Okay. And I would notice that the number of unpaired electrons are 0 here, which makes it diamagnetic molecule or complex. And hybridization wise, we identified it is sp3. Correct? It is sp3 hybridized in this case. If you compare initially when you have nickel, the configuration is 4s to 3d8. Acha. In case of 4s to 3d8, what you would notice is that in case of 3d8, there are two unpaired electrons present. There are two unpaired electrons present. But now the number of unpaired electrons have become 0. When the number of unpaired electrons decreases from the original value, then we call such complexes as low spin complexes. So this would become one of the low spin complexes. Clear? Everyone? I hope all of you got this, right? So why don't we all do it together? One more question. So try this. If you have FeCO5, let us see how we can do that. Everybody check. If you have FeCO5, let us try to figure out how we can get the hybridization and its magnetic behavior. In this case, check iron is 26. So 4s2, 3d6. Originally, we have 2 electrons in 4s and 4 unpaired electrons. We will, as the ligands approach, we will club them up to make it 3d8. So 4s, first let us write 3d. In case of 3d, 8 electrons, being a strong field ligand, we'll always try to pair them first and see what we can achieve out of it. So after pairing, this is 4s, sorry, this is 3d. And then 4s is empty and 4p is also empty. 4d is also empty. How many do I'm supposed to accommodate? 5 of them. So I can see that I could use these 5 to make a reasonable hybridization, which is DSP3. Okay, DSP3. Now, DSP3 can be identified as two types of orbitals. One is sp3d with z square. The other one is sp3d with x square minus y square. So iron in this case would have this type of geometry. First, it could make this type of geometry, which is trigonal. This is trigonal bipyramidal. And trigonal bipyramidal typically is formed when the hybridization is sp3d. Sorry, I mean d dz square and sp3. Let me rewrite that here also so that there is no confusion. Because it is the inner orbital, I have to use that d first and sp3 next. Okay, this. In fact, this would keep changing as well, where we will have iron this way with a pyramidal shape. Okay, you can see it is a square pyramid also. So when you have it in a square pyramid, now the hybridization is d x square minus y square and sp3 combination. Okay, major time this would be existing in this form, and if the question is typically asked and options are given, then you go for this one, trigonal bipyramidal. But if the question is asked what are the possible hybridizations, then you write both of them. Okay, it could be DSP3 with Z square or DSP3 with this one. So one is trigonal bipyramidal, other is square pyramidal. Here everybody. So this is how you need to identify the hybridization. What are the properties now? How many number of unpaired electrons we found? 0, correct? So which means number of unpaired electrons have changed. Next, is it a weak or low or high spin? Low spin complex, correct? Now, when an d orbital is present in the hybridization, and if you are using inner d, that means 3d, and then using 4s, that means you are using an inner d orbital. Therefore, such complexes which are formed are called inner orbital complexes. So this is one of the inner orbital complexes. Inner orbital complex. This type of information we should be able to fetch for carbonates. Clear? Any doubt, everybody? Clear on that? Right. Next. Let us see. I mean, this is all the IUPAC form. There are few compounds which I have given. Let us immediately recall orally what are the rules for IUPAC and then we'll write them. Okay. The first rule for IUPAC is that you should always write the naming from positive side, positive charge towards negative charge. We cannot write anything which is negative first and positive next. Okay? Always positive part should be written first, then the negative part should be written. Clear? Next, we should, while writing names within the coordination sphere, within the sphere when you are writing, we should always write ligands first and then metal name next. Within the ligands, we should always follow alphabetical precedence of their name. Clear? Numbers will not get any precedence. That is di, tri, these kind of cases will not get any precedence to that. Clear? We have to represent the oxidation state of the metal in a stock notation. And between inner and outer sphere, right? That is ionic sphere and complex sphere, you should always maintain a small gap. Right? These are the basic fundamentals which we take care of. And based on that, let us see Why don't we write together, everybody? This will be practice for you. See the first one. Keep writing. What would be the first one? Potassium, then space. Entering into potassium. Then what is the next thing we have? Hexa, hexa, cyano or cyanido. Both of them are correct. Cyanido. Okay. And then what is that? We have, this is where the catch is. If the complex is a negative charged, then the metal name should always be the Latin name ending with 8. Latin name ending with 8. So this is hexa cyanidoferrate, ferrate, which is the Latin name. And then close that with a bracket. What is the charge we will write? Check out the oxidation state, which is +2. That's it. This is where you will end it. Here, everybody. On that basis, write the next one. What is the name now? That. So potassium, hexa, chlorido, right? Platinate, platinate 2. Next one, platinate 4. So next. Next one, this is hexa amine. How many M? 2M here. Hexa amine cobalt, common name. Now, when you have cationic part or the neutral part, we always use common name. So on that, we will have +3 space and then chloride. Outside name is only chloride. Next one. Next, this one. What is the name? Chlorine and water. So aqua should be given preference. So what is that? Tetra, aqua, and then dichlorido, dichlorido, chromium +3, and outside we have chloride. Outside we have chloride. Okay, complete the rest. Hmm. Pentaamine chlorido ruthenium. How much is the charge? 3 ion. Next. Ethylene, right? So there are 3 of them. So what should we write? Tris, correct? Right, tris. Tris, ethylene, diamine. Only one M, important. Okay, here it is only one M. Tris ethylene diamine with ferrate. Ferrate 3 outside chloride. Hmm? Because it is anion. Huh? So that is to be iron 3 and then chloride. Next, nickel. This is bis glycineto. And what do we have? Nickel 2. Done? Say it again. Usually, what would happen is when you have NO with a strong fields, they exhibit NO plus more than neutral. Okay. What beta? Either ways, it will have it. If you have it Na3 there, isn't it? If you have Na3, if it was Na4, then it would show plus 2. Got it? Achha, even if you have neutral NO, suppose if you have neutral NO, what would have been the charge there? Because neutral NO is a 3 electron donor, isn't it? 3 electron donor means again you'll have similar thing only. Clear? Check. If you notice bridge ligands, in case of bridge ligands, these ones which are bridging two metals, they should be represented as mu. So that will become mu amido, mu hydroxo, then tetra aqua, iron, sulfate. Okay. I hope all of you got that. How do we represent the mu forms there? Clear? Any doubt? Right. Okay. So again, going back to carbonyl compounds, see, I would suggest you remember it like a table and what will be the number of CO bonds we have and all of that. See, first metal, carbonyl, and then number of number of terminal CO groups, how many we have, and number of bridged CO groups, how many we have, and lastly, how many number of metal bonds, bonds. If you have bonds, how many we will have? Okay. Now, for starting with this NiCO4. Achha, first let us List out all the important carbonyl compounds which we'll be learning. So write down nickel CO5, FeCO5, Cr CO6, and M2, sorry, Mn2 CO10. Okay. Then Fe2 CO9. This is another one. CO2 CO8, right? And CO2 CO8 both in solid state and liquid state. Liquid state and solid state we have slight differences. Then Fe3 CO12. These are typically the ones which we'll be learning. So make sure that we are aware of how many terminal groups we have and how does the structure looks like, what is the hybridization. So first check out on the hybridization. We learned about first two, sp3. This one we got it as dsp3. Okay. Next one you'll get it as d2sp3. Correct. And in manganese also you'll get d2sp3 involving the manganese bond also. So it is an octahedral structure. Keep that in mind. So it is an octahedral structure is what you'll have. Next, Fe2CO9 will also have D2sp3, and this we will have DsP3 here, and in solid we will have D2sp3, and here we'll have D2sp3 again. We'll have D2sp3 again here. Okay, I'll show you the structures also. So first let us understand this part. Now, number of terminal, there are 4 here, 5 here, 6 here, and 5 on each side. 5 on each side. Okay. 4 on each side. 4 on each side. Yeah, sorry, 3. 3 on each side. The center again will have 3. Here 4 on each side. Here. Here 3 on each side in solid state. And lastly, we will have 4 on each side, each of iron. Okay. Clear? Next. Number of bridge bonds. How many we'll have? Here there are no first 3, there are no bridge bonds. Okay. Manganese, there are no bridged CO groups. In iron, we will find 3 of them. In iron complex, we will find 3 of them. In liquid state, we will not find anything. In solid state, we will find 2 of them. Here, we will not find anything. And lastly, metal-metal bonds. Here, these are not valid. Here, there is one manganese, there is no. In manganese, we have one metal bond. Iron will have one metal bond. Cobalt, one bond, and here we'll have 3 bonds. Okay. Clear? Please practice this. This is one very, very important area. Carbonyl. I remember I couldn't discuss a lot of carbonyl compounds when we last had a theory, right? That's why I'm discussing it again. Stretching frequency, how the structure looks like, how the metal carbonyls are, how the EN value need to be calculated. These all things should be very clear with carbonyl compounds. Okay? Check out structure wise. Okay? First, we'll start with the bottom here. So first Fe, and need more space for this. Take another Fe here. Okay. So these 3 will have a metal-metal bond in this case. Clear? And we will have 4 of the kinds here. 4 of the CO groups here. Okay. Here also we'll have 4 of that. Here also we'll have 4 of that. CO, 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 and CO, 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 and CO. Right? What is the hybridization in all of them? That is D2sp3 combining with the other orbital. Now, what is this sigma bond, everybody? This sigma bond, the sigma bond formed in between them is between D2sp3 orbital versus D2sp3 orbital, overlapping. This is the sigma overlapping which will have. Got it? I think this part is clear. Right, next. Let's see CO CO8 solid. So we have cobalt. Cobalt will have one bond here. Then we will have C double bond O, which is a bridged form. Another C double bond O, one more bridged form. Rest all three will be carbon monoxides here, like this. We'll have three carbon monoxides form. Done. So that would be the next form, which is in a solid state. Again, if you compare the hybridization, these all the sigma bonds on this side, sorry, not this one, this one. This is the sigma bond between them. That is between D2sp3 with D2sp3 overlapping. And in solid state, usually, because to keep it more compact, this molecule will always adapt the bridged form. Okay. But in liquid state, it will have only one connection here. So that is CO and CO, that metal connection. And then rest of the four bonds would be outward like this, which is having terminal carbonyl molecules, terminal carbonyl compounds here. Okay. Yeah. Now, suppose if I call this as L2 and this is, if at all I call this as L1. Now, because the carbonyl compound is making a bridge also, the overlapping will increase here. So what happens to the length? Decreases. So L1 typically is greater than L2. By chance, if this is asked, please be aware of it. Okay? And the type of hybridization is same here. I mean, type of sigma bond is same here. D2sp3 and D2sp3 overlapping is been observed in both of them. Clear? Done? Right. Next. Huh? And D2. 5 or 6 we have. No, sorry. Here it is D only. 5 only we have, no, but links. It is DSP. DSP3 and DSP3. Okay? DSP3 and DSP3. Okay? Wait, let me show the analysis also. That's better because orbital wise how it looks like. We'll see that also. See, cobalt has 27 electrons, which makes it 4s2 and 3d7 originally. Okay. Now, what we are doing is we are pushing out electrons towards 3d. So, how much we will get here? Sorry, as we push it, so we'll get 4s0 and 3d 9 we'll get, right? So, in this 3d orbital, 1, 2, 3, 4, 5. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 electrons are present here. And we have 4s empty and we have 4p empty. Okay. Done. So now imagine mixing this one cobalt here. Let me copy the same thing again and put one more cobalt here. Done. This way. So what are we doing? We are mixing DSP3, DSP3, correct? So when I mix DSP3, what am I supposed to get here? I'm supposed to get two type of orbitals. What is that? Either it should be dz square sp3 or d x square minus y square sp3. Clear? Now to accommodate four carbonyl compounds and only one bond outward, which one is best? Square pyramid is better, no? So which orbital do we mix here? X square minus y square. So let us mix that. So d x square minus y square plus sp3. Here also dx square minus y square plus sp3. Okay. So on mixing both of them, then what am I getting here? On mixing both of them, then I'll get cobalt with this orbital, and then we will have this four carbonyls like this, right? This way. That, and the next molecule of CO will also have this way with one orbital coming on this side. Okay. So let me put actual orbitals rather than lines. So this is how the orbital will look like. This is the hybridized orbital. Same way, these are those hybridized orbitals. Okay. So as we bring this closer, what will happen? They'll start overlapping. Done. So this bond, this sigma bond is between D sp3 and D sp3. Got it? Everybody clear on this point? Right. Now notice another factor which will always be asked is to calculate EAN value, effective atomic number. By formula, EN means atomic number minus oxidation state plus 2 times of number of ligand connections. Correct? This is the typical formula for EAN. Now, atomic number of cobalt is 27. Oxidation state is 0. Clear? And 2 times of how many ligand connections I have? How many ligand connections I have? Notice this now. So we have uh, 2, 4, 6, 8. Per cobalt I'm asking. Per cobalt, how many we have? 8. Correct? Now, this was a single electron which was shared by cobalt. So you will add that extra electron for the bond. Understood? Clear? Alright. Each cobalt has used one electron. See, go back and see the orbital. See, there is one electron present in this. If I put the orbital here, this is the hybridized orbital which we have. In this, there is one electron present, no? So, in the valence shell of cobalt, how many we will have now? We will get one pair from outside, one pair from here, one pair from here, one pair from here. And this will be the one electron which is which itself is contributing, right? That cobalt is only contributing. So while calculating that En factor, you will have to add that one also. So check out. So how many we will get now? Each has each has 4. So how many have added? 4 only. No? Acha, ligands, number of 4s. Ligands are 4, yeah. Okay, sorry. So how much we have here now? 28 plus 8. So which makes it 36. Which means it is strictly following En value. And this is something which you need to address everybody, that when it comes to carbonyl compounds, definitely we need to have En followed in all the cases. Okay. Yeah. Based on that, can you figure out what will be the En value of iron in this case? Check. That will also become a practice for you. EAN value here. Say it again. Solid state what? It's not matching. How to calculate? Achha. Let's see. So we'll check out in the iron case now. First 26 minus 0 plus how many number of complete ligands we have? Complete ligands. Four. Four of them. Isn't it? Plus how many metal bonds it is forming? Two. Two of them. Isn't it? Check out whether it is matching or no. 28 plus 8. So 36. It is matching. Right? Check out here also. En in this case. 27. Okay. Plus how oxidation state is 0 plus 2 times of how many actual ligands we have? 3. Okay. Terminal ligands. You should always count first the terminal ligands. Plus how many connections it is giving? 3 more. 3 from a sigma bond point of view. Okay. So how many we can get? 3. So how many we have here now? Check out 27 plus 9. 27 plus 9. So how much we are getting? 36. Yeah. Okay. Here also it is match. Now clear? Every time there is a sigma bond forming, you should always count one electron from itself because the metal is giving that electron for sharing. But it is not doing the same thing when a lone pair is coming from carbon monoxide, right? There it is using an empty orbital. Okay? Everyone clear on that? Right. One more which was remaining was manganese. Let us write for manganese. Mn2CO10. Okay. In manganese, we will have Mn bond here with 6 of them this way. So basically, we are making an octahedral structure, isn't it? So to accommodate that octahedral structure, we need to make D2 sp3 hybridization. Clear? So only one single electron I have to keep it. So manganese by configuration also, it is 4s2 3d5. So if I push all the electrons, so I'll get 4s0 and 3d7. So in that 3d7, 1, 2, 3, 4, 5, 4, 1, 2, 3. Okay, this is 3d7. In which how much I need to keep? I need to keep only one unpaired electron. So I'll pair the first one, keep one unpaired electron here. Okay, keep this as one unpaired electron. And then you have 4s being empty, 4p being empty. So this is 3d, 4s and 4p. Now mix all of them. So from here to here. So what do I get? D2 sp3. And in that D2 sp3, this is how the orbital will look like. Correct? In which there is one electron present. Right? So that electron will be used for bonding. So CO, CO, CO. Right. This is the structure for Mn2CO10. Huh? Everybody clear on that? So go back to the table once again. Check if everything is correctly sorted. Oh, we forgot to write one more structure, I guess. Which one? Iron. Let us write that iron structure also. Fe2CO9. Fe2CO9. In Fe2CO9, structure is Fe and Fe we have. One, this is called ketonic link because it is like a ketone which you have. Okay, C double bond only. So one ketonic link here, one ketonic link here, and another ketonic link we will have coming out of the plane like this. And then we will have 3 complete terminal carbonyl groups we have like this. Got it? And you can notice the hybridization in this case, guys. I need to accommodate 3 bonds now. Okay, 3 sigma bonds. So original configuration of iron, which is 26, which is 4s2 and 3d6. I will push the electrons to make it 4s0 and 3d8. Now in this 3d8, if you notice 1, 2, 3, 4, 5, I need to keep how many unpaired electrons here? At least 4 of them. Metal-metal bond will always exist. Got it? 4 of them need to be kept unpaired. So 1, 2, then 3, 4, 5, 6. Okay. So how many we should have? 3. One is PD. 8 we have, right? So 1, 2, 3, 4, 5. So 8. Let me put this 8 one here. 7, 8. Okay. Let me mix all of them first. This is what we have. And then we have 1 4s. Then we have 4p. I need to mix 2d. I need to ensure that. Okay, got it, got it. See, what we can do here, remove this one, keep it 1 here, and keep it 1 in the S. Okay. Now, mix this from here till here. Okay, mix this, all of them. Got it? Everybody? So, on mixing it, what do I get? I'll get D2 sp3. Okay, first I'll get D2 sp3. So in that D2 sp3, there are orbitals forming this way. 1, 2, 3, 4, 5, and 6. Okay, so we'll have 6 bonds forming this way, and in that we will have 1 electron on this side, 1 electron on this side. Total 3 electrons are present in here, isn't it? So 1 electron we can keep it here. All right, 1 electron we can keep it here. So now if you compare, 3 only we should have, no? 3 have gone. Right. No, it's fine. Check. So these 3 bonds we require. So I'll write the same 3 bonds here on the other side. Yeah, like this. Check. Now, this one, as they start to overlap, this will go towards 1 C double bond O. Understood? This will go to 1 C double bond O. This will go to 1 C double bond O. Clear now? Between metal and metal this time, it is the pure d orbital which is combining. Understood? There is 1 electron in d orbital. Let me show how the d orbital looks like. That is a pure orbital. That pure orbital will be like this. You know, typically that pure orbital will be like this. That is not hybridized, remember. This one is just dxy, and this one is also dxy. And there is a bonding between dxy and dxy. What type of bonding we'll get? Delta bond. Remember that? What do we get? Delta bond in this case. So we'll have this one like this. If this is your z-axis, then what are these two? dxy and dxy. So between these two, we will have bonding here. This one. What is this bond now? Delta bond. So there will be one delta bond. So important to note that here we have dxy, dxy delta bond here. Okay. While rest of these are all sigma bonds. The sigma bonds are between D2 sp3 D2sp3 and D2sp3 overlapping. D2sp3 and D2sp3 overlapping. Okay. Now check out what about the uh, EAN value now. How much is the EN value now, guys? 36. Now we have 26 minus 0 plus 3 into 2 plus how many unpaired electrons? 4 of them. So 26 plus 6 plus 4. So that makes it 36. So the EN value for that is matching. Here. Done. We'll stop it here.